Hi, welcome to online tutorial videos from JCBRO Labs. For more information about JCBRO, you can visit us our website, which is www.jcbrolabs.org. So, in this video, we will talk about how to implement a real-time filter, and that is specifically the IR filter using Arduino. Further, we also provide online training, help in technical assignments. We also do freelance projects and industrial projects based on data science, Python, machine learning, embedded system, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrolabs.org, or you can also mail us at info@jcbrolabs.org. Okay, so let's first go through some of the basics of the filter, which will be very important while writing the real-time filter code for the Arduino in embedded C. Okay, so let's move to our basic. Okay, so right now for this session we are using a camera. Okay, so when we talk about a filter, so filter, as you know, filter are defined by their transfer function. So h of z is given by, for IR filter, it is b0 plus b1 z inverse plus dot dot dot. So it can go up to plus b2 z minus 2 plus b3 z minus 3 and so on. Similarly, the denominator part will be like a0 plus a1 z inverse plus a2 z minus 2 and dot dot dot. Okay, so if we write a time domain representation of this filter, because ultimately we have to implement, we will be implementing the filter in time domain. So it will be like y of n plus a1 y of n minus 1 and dot 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 equals to, okay, here you can put a of 0 plus b0 x of n plus b1 x of n minus 1 plus dot dot dot. Okay, so this will be the time domain representation of the filter, and we will be implementing this particular equation in embedded C code. Okay, now there are different coefficients, so you can think about this filter here, the h of z or the filter. So our input is x of n and our output is y of n. Okay, now coming to our concept of for this video. Okay, so in this video we will be we want to implement a fourth order filter. We will be implementing a fourth order filter, but we will be implementing this filter as a cascade form of two filters. That means second order one filter and the another second order filter. These will be in the cascaded form. Okay, so here will be our input x of n and here will be our output y of n. So this x of n will be our real data which we will be acquiring directly from the function generator, and the filter output will be the y1. So this form we will implement it. So the transfer function or the time domain equation for this for 1 second order filter will be like we can say it as y of n equals to b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2, right, plus a1 y of n minus 1 plus a2 y of n minus 2. And this is true when our a0 is equals to 1. Okay, so we are assuming that our primary coefficients, this a0 is equals to 1. Okay, now so we have to identify these coefficients b0, b1, b2 and then a1 and then this coefficients a2. We will be using the Matlab program in order to identify this particular coefficient. So basically, this video will be a two-part video. So in first part, we will be writing this Matlab code, and we will be identifying these different coefficients. And then in the second part, we will be implementing it in a real time. Okay. So now, first of all, further, most of you will be aware that when we talk about digital filter, so in digital filters or in DSP, the sampling information FS plays a very critical role. Okay, so prior to designing this filter in Matlab, we should be knowing about this sampling frequency. So this sampling frequency means how we are getting the sampling frequency on the real hardware. So now coming to the hardware structure. Okay, let's plot the hardware structure. So a hardware structure will be like, here we have this Arduino, and the input is from the function generator. So I hope all of you know about this function generator. It will be generating some function of any specific frequency, and then it will data will go to the computer through serial port. And on this computer, we will show the waveform in Arduino serial plotter. So in Arduino serial plotter, we will be showing the filtered waveform. Okay. So now when we are going to this Arduino to sample the data, so we have to know what sampling frequency can be achieved from this Arduino in real time, so that we can use that particular sampling frequency in our Matlab code in order to generate the filter coefficients. Okay, so yeah, that's cool. Now one more thing in this, we will be doing here the frame by frame analysis. So frame by frame analysis means we acquire some data of a specific length. So in this case, we will be first acquiring 256 or 1000 samples. So first we'll test it with 256 and we will expand it to 1000 samples. We will pass it to filter, and then we'll send it to computer. Okay, and then we will again acquire this, we will filter it, send it. So this process will keeps going on. So this 256 this 256 samples can be treated as one frame. So we will be acquiring one frame, processing it, and then sending it to the computer. So this is how we will be doing this entire process. Okay, so now let's get familiar with the hardware and with the entire setup. So this is our setup. Here we have our function. This is the DSO. Here's our DSO, and here's the function generator. Sorry for the light intensity. We won't be able to see what exactly written in it. I will be describing it to you. And here is our function generator. So we will be visualizing the waveform generated by this function generator on this DSO. And here we have our Arduino board. So these leads are connected to the inputs of this Arduino, right? And DSO lead is connected to the function generator as well. So first task is to test our waveform, whether our CRO or this DSO and this function generator are working fine. So what we'll do, we will connect the lead of this function generator and DSO together, and we will see if there is any frequency which is being generated by the DSO, generated by the function generator. Okay, so let's connect these signals together. Here it is. So right now this function generator is generating some triangular wave. So let's smooth it out. Okay, so change the function. because we want to I think I have increased the sweep. Change the function. This is the square wave. DC. Here is the sine wave. Okay, so right now we are generating the sine wave, and the frequency which is being generated is 276 hertz. So 276 hertz is being generated from this function generator. So we'll showing you the waveform like this. Okay, so now because we have connected the leads of this function generator DSO together, so we were able to show you the waveform. So right now what we'll do, we will do a simple test, because our first task, remember, is to obtain the sampling frequency from this Arduino. So we want to know what exactly sampling frequency we are getting. Okay, so what we'll do, we will do a simple test. We will sample the data. We will write a program in Arduino which will sample some data from it, and then we will generate, or we will toggle the LED, built-in LED at pin number 33, and we'll show we will see the waveform which is coming at this pin number 13. Okay, so from there we can understand what is the sampling frequency being provided or being available to us from this Arduino. Okay, so let's go to the Arduino now. So we have connected, we have set up, we have connected our setup. So DSO is connected to pin number 13, and function generator is connected to A0, and that's why we are not getting any output on DSO, because we are not generating anything on pin number 13. And then one thing should be taken care of during this entire experiment. All the grounds should be common. Okay, now coming to writing a code. Okay, so we will come to the Arduino part. So here's the Arduino code. We have saved this Arduino as a filter live, as the name of this filter live. Okay, and first of all we will set the pin mode of pin number 13 as output, and we'll set the pin mode of A0 as input. Okay, we'll save it, and then we will send the data to serial port as well. So serial dot begin with 115200. Okay, now because right now what we want to do, we want to acquire the data, and we want to see what sampling frequency we are getting. Okay, so we will create array in order to record the entire data. Okay, so we'll create an array of float type, float data, and of 256 samples, because remember at the starting we'll test with 256, and then we will define int I as well here. Okay, so here now first of all we will record the data. Okay, so for I equals to 0 to I is less than 256. Okay, in order to make it more user friendly, we can define the signal length and then I plus plus. Okay, so I know we have to define signal length here as well, so has define signal length 256. Okay, so here we can also define it like signal length 256. Okay, now data of I equals to analog read. So I think we have, okay, analog read A0, yeah, and we will convert it into the corresponding voltage. So we will multiply it 5.0 and 1024. Remember, this Arduino can only get the data from negative, from 0 to plus 5 volt, right? So your function generator should have some threshold. So all the waveforms should be above 0, all the voltage, and the same you might have seen during the setup portion. That means the waveform coming from the function generator was above 0. Okay, so we have set it. Okay, now we will change the digital write pin number 13, right, and we will define it as a state. Okay, so here we will define a state variable so that we can toggle it again and again. So state state equals to 0x01, and we'll define like int. Okay, and let's change it to, yeah, state equals to let's do XOR with this one. Okay, so let's check. I hope everything is fine. Let's check. So right now we are not sending the data to the computer, because otherwise we will have some problem while reading the sampling rate. So right now it is simply reading the data and then toggling the pin number 30. So toggling is toggling clock, because our Arduino is running at 16 megahertz. So this toggling will take a very fraction amount of time, because it just consumes one clock cycle. Okay, so it will not have much effect on our sampling rate. Okay, so let's compile and upload it. Our Arduino is connected to COM8. Okay, so it's compiling. Hope so we don't get any error. Okay, and we are not getting any data on CRO as well. Let's see to, okay, we are not getting any data. That means this pin number 13 is not toggling, I think. So oops, it may be possible that I have 8, 9, 10, 11, 12, 13. Yeah, now I changed the connection, so I wrongly connected. Okay, so this red one is from function generator. Okay, and then this blue one is from to DSO. So here DSO we are getting this waveform. So if I expand it, okay, you will get nice square wave. Okay, because it is obvious this just pin number 13 is getting high and low. Okay, so here it is saying 4.46 kilohertz. So this square wave frequency is 4.46 kilohertz, which indicates, because this if you see the code properly, this entire for one this pin number 13 is toggling at every instant when data is taken out. Okay, so if this frequency we are getting of 4.486 kilohertz, that means the data is being captured at double of that. Okay, just keep in mind or try to understand it. The data is being captured at double the rate of this toggling clock. Okay, so right now this frequency is 4.46 kilohertz. So we will try to put some delay so that we can get exactly 4 kilohertz frequency of this toggling frequency, 4.4 kilohertz, and then we can get the entire sampling rate around 8 kilohertz. Okay, so we will provide in delay in microseconds. So I tried it earlier, and if I provide delay of 13 microseconds, then it will be very much similar to the 8 kilohertz sampling frequency. Okay, so yeah, and that's good. Now let's see. Okay, now let's burn it and let's see the uploading done, and let's see the output of function generator. So now our frequency of this clock is 3.9 kilohertz. Okay, so it is 3.9 kilohertz, which is very much near equal to the near about to 8 kilohertz. So in our all computation, we will take the sampling frequency for filter designing as 8 kilohertz. Okay, so now we will do some changes in the code as well. Now we will sending the program to a computer so that we can see what kind of waveform we are getting. Okay, so let's send data to the computer for I equals to 0 to I is less than signal length. So serial.println and we're sending data file. So now first it is capturing the data and then it is sending it to that particular frame to the serial monitor. Also on serial monitor we will seeing some waveform. Okay, so now our sampling is done, right? So our function generator work to pin number 13 is done, and we know from this code we will get a sampling frequency of 8 kilohertz. So now we will connect our function generator to the DSO pin to the function generator pin so that we can see the waveform which we are passing to the Arduino. Okay, so here it is. Okay, it was already there. So both the pins should come together now. Okay, so function generator is passing the data to Arduino as well, and DSO is also taking the samples of the function generator as well. So as I see, so this is the waveform which is being generated by the function generator. Okay, 277 hertz. Okay, and if you look at it carefully, it is above 0, which I mentioned, like the waveform, the data waveform generated from function generator should be above 0. Okay, so now let's burn this data to the microcontroller. Okay, it is showing some error. Okay, oops. Okay, let's burn it again. Okay, done uploading. So uploading has been done. So let's see waveform. Okay, so here is your waveform on the serial plotter of this computer, and it is very nice waveform, right? And it is very much similar to the waveform which is being generated from the function generator. So right now Arduino is sending 256 frames from the function generator and then sending it over to the computer so that we can see. So right now we have not applied any waveform, so if you look at the amplitude part, it will remain constant. Okay, so now I am changing the frequency. Okay, let's put all these things together on the same graph if possible. So let me do that here. Okay, so now you will be seeing this waveform, all the hardware at the same place simultaneously. Okay, so now I will be changing the frequency from function generator, and if we observe, the frequency has been increased, so it has shrunk to the serial monitor. Okay, further. Now the frequency is 1.8 kilohertz, 2 kilohertz. So remember the Nyquist criteria, the sampling frequency should be twice to that of the original frequency, right? So right now remember we are sampling at 8 kilohertz, so it can visual show the corresponding frequency up to 4 kilohertz only. Okay, so now if I try to increase the frequency range, okay, now we are getting 26.39 kilohertz. It's way higher than the Nyquist criteria, so I try to reduce it. You will see the different phenomena. Whatever in theory you have learned, you will see all those phenomena here, the aliasing phenomena and all this. Yes, now it is by it had passed. It is 7.35, 7.4. So it is a kind of aliasing phenomena. Okay, it is has increased to 7, 8. Yeah. Okay. So now coming back to our frequency range, it is 2.7 hertz. So it is too high. We are not able to see it. So because we can't change the x-axis of this serial plotter right now. So that is why I will tune my function generator for lower frequencies only. Okay, here. Now you might also have been observing these small peaks in between. So that is because it has just generated a frame and then transmitted over. So that's why this transition is occurring. Okay. So I thought I can design the MATLAB filter here in this video as well. Sorry. So I will create the another video for MATLAB filter design in continuation of the same, and then we will move forward. Okay. So that's it for this video, and wait for our second part in this real-time filter design using Arduino. Okay. So thanks for watching, and please share this channel and subscribe to us. Further, we also provide online training, help in technical assignments. We also do industrial projects based on data science, Python, machine learning, etc. So if you have any requirement, then you can contact us through our website, which is www.jcbrolabs.org, or you can also mail us at info@jcbrolabs.org. So that's it for this video. Thank you. We're coming up with the second part.